Surely there's been a time, maybe in your classroom this year, maybe in a former year, or maybe even when you were a student, where you thought to yourself, or they said out loud, why do I even have to learn this? Why do I even have to do this? And maybe orbital diagram filling and electron configuration writing fell into one of those buckets.
Yes!
In today's video, I hope to prove to you that you can develop and design lessons. Not just chemistry teachers, but any science teacher out there watching, you can develop a lesson wherein your students' skill practice and review becomes very purposeful in the emergence of a pattern or in data analysis. That's what I'm all about here. I want to get you to the place where you are building lessons that are always engaging students in the process of science. So in the case of building orbital diagrams, writing electron configurations, that's where the process starts, but then they're going to use those as evidence. And that's what we're talking about today. This is what I believe the sum, anyway, of the collaborators who devised the NGSS were thinking when they set out, for example, patterns as a main cross-cutting concept of science and called that out as something we want to include in lesson planning. And even if you are not accountable for following the NGSS or any state adaptation of it, it's still an amazing thing to incorporate to keep class time active, to keep students highly engaged and with a high expectation for them that there will always be something for them to actively do, that they will never be expected to just sit and passively suck in information into their brains, because that's not how brains work. If we've not met yet, my name is Lisa. I've worked 15 years for an online cyber school, but I have passion for teaching true science. And obviously my hands were tied there. So after years and years of frustration, just literally feeling like I was talking at my wall, I decided that I had to change things. I didn't care what the status quo was. And surely I could make learning happen in a scientific thinking way without the traditional tools that you would think of. And I feel like I was reasonably successful in that effort. Today's lesson is, I think, a glowing example of it, because what I did to come up with this lesson was, at the very beginning of the year, decide a conscious, committed, all-in commitment to making every single day in my classroom a day where students were held to a high expectation of learning, that they were going to produce something that showed their understanding or their skill that I could use to evaluate, but more than that, allowed them to have or keep what we would think of as a conventional science notebook and realize that science is about being wrong. And if I wasn't giving students the opportunity to be wrong, they actually weren't even learning science. So it's much less of a fact-driven, information peddling approach, and much more of a student-centered, inquiry-based approach where we're learning together. And mistakes, they're expected to happen. All right, as we dive into this lesson, there's a few things I like to do first when I'm preparing one of these videos. The very first thing is to let you know where it lands in my sequence of lessons. This lesson, it's very important to let you know that my students at this point in time have been introduced to the orbital box diagrams. They've been introduced to electron configurations and the Schrodinger model. I do have a separate lesson on that introduction, which relies heavily on a free web simulation, and what I would consider much more loose or less guided inquiry for that particular lesson. So it's in this lesson that students are really hunkering down, buckling in, and following the guidelines that we have extracted in that first lesson. What do you think we have to do to build these on our own? And now they're doing it. They're building these on their own. Also, prerequisite to this lesson, as it has been prepared and as I'm going to share with you, are two lessons related to Bohr's model. The first one, basic Bohr model, how electrons behave and where they live within an atom. The second one, all about atomic radius and its periodic trend on the table. And so as soon as we open up the very first part of this lesson, you're going to see a call out, a reminder to that atomic radius piece. Now, the next thing I like to do is make sure we're all talking about the same intentions. So the learning standard in the NGSS, and I am deferring to the NGSS here because there's so many states that have adopted it. I think we're looking at 38 or 40 now, or some version thereof, that it seems to be the tie that's binding us together, rather than if we just look at one particular state set of standards. So this standard falls under the umbrella of structure and properties of matter, using the periodic table as a model to predict the relative properties of elements based on the patterns of electrons in the outermost energy level of atoms. Also within the NGSS, of course, and really what's driving this lesson as an active learning, inquiry-based, student-centered lesson is the incorporation of science as practice and cross-cutting concepts. So the NGSS calls out for science and engineering practices here, developing and using models naturally. But also, I think what I want you to look for in the lesson we're about to review, and I will try to point out for you when it happens, is also that it's built in a way for students to obtain and evaluate and communicate information while in the process of doing this modeling work. And then in using their review and practice models as evidence, they can argue some positions. They can argue, you know what they're arguing? They're arguing core ideas. That's really what they're arguing, because there's no lecture going on in this lesson. For the cross-cutting concepts, there's really only one. In many of my videos and many of my lessons, when I've mapped them out, look at them really closely, I can identify multiple cross-cutting concepts for each lesson based on what I'm asking students to look at or do or think about. In this lesson, it's absolutely 100% patterns, perhaps a little bit of system and system models in there, but what shines is the pattern. And that's really what we want students to see in any lesson focused on periodic trends. The last thing I want to mention before jumping into this lesson, if you've not heard me share it before, is that every single one of my lessons are going to follow a specific 5-part framework. And if you're familiar with 5E, I would challenge that it's similar to 5E, but traditional 5E lessons, often used in middle school, they last a long period of time. Over several days, we do these 5 steps of engaging, and I forget all the E's, honestly. they got by me right now. But in the high school, in biology, chemistry, physics, earth science, you have lots and lots of core ideas and skills, disciplinary literacy-based skills to include and accomplish over time and train. It's really necessary to go a little faster than spending all week on a core idea. And so these lesson frameworks include soup to nuts. First, a review and preview, which is my warm-up. It is a practice opportunity for students to get feedback on their current understanding in a way, however, that always connects to the upcoming lesson. So we're not just doing something random. We're not spiraling for the sake of spiraling. We're activating and integrating the prior knowledge that they should have. Then, of course, we're presenting some lesson objectives, but in a student-centered fashion, we're using learning intentions and success criteria. We're giving students that why that they're looking for. Why do I have to learn this? In this case, for today's lesson, it's because it's the justification for chemical properties and chemical change. But the series of things they're going to do, the success criteria for this lesson, will range. And it will range from what they are actually going to do during class time, an activity-focused success criteria, as in I engaged today, and an assessment-focused or based success criteria, which leads them more to question themselves, how well do I know this? How much or how differently do I have to approach my learning? What decisions do I have to make next to master this? Or where am I on the range of mastering? Once you've presented those goals to students, then they jump into an activity. There's sometimes, often, a word wall where I will just, give a nod to these are the things you'll see, or these are the terms we're trying to explore, the core ideas. But the amount of lecture is so minimal. You throw them into an activity with some very specific instructions, depending upon where your students are with things. This is the place where we can differentiate and apply different levels of guidance to the inquiry to customize it for lower level learners or high achievers, and giving them an artifact outline to go with those task instructions. Usually pointing students to some other third-party site or video or text to work with to extract what they need to extract, and making sure those artifact outlines are really strategically designed to facilitate and to guide that learning. The real hard part of science, which is usually using evidence to analyze, using evidence to argue. And then finally, that assessment-based piece, we really want them to be able to leave class confident that they can do the skill and ace the test from the activity, and never leaving them feeling, the goal here is never to leave them hanging, is always to get them to do the comfortable struggle and then come out of it with more confidence.
Oh, yeah.
Because what comes next should honestly be easy. That's the design. That's the idea. That's the approach. Let's take a look at electron configurations on the periodic table. This lesson begins, as I said, with a review and preview, specifically here of energy comparisons within orbital diagrams, within Schrodinger's model of the atom, and electron configurations. There's really 3 parts here, and honestly, especially when you have a range of abilities in your classroom, a review and preview with multiple parts is fantastic, because with either multiple parts or repetition is super fantastic, because it ensures that even if students don't get through the whole thing, they have reviewed and activated the prior knowledge they need, and you're able to see at the start of the lesson, where do we go from here? Am I ready to do this lesson coming up? Do I need to do more work with this or not? So it's almost like an exit ticket at the start of class also. But you can see here in the realm of what we're doing today, which is tying electron configurations to the periodic table, coming off of and learning and practicing filling orbital diagrams, this is highly relevant. So the whole off-bow rule, the off-bow principle that we have to fill orbital boxes or energy levels before moving to the next makes comparison of energy levels something they need to know and be able to do. So there's a series of comparisons here, making sure to compare different energy levels with the same shape, like an s orbital, or a p orbital, to compare the different shapes in the same energy level, so a 2s and a 2p, and then totally randomizing it so that they could see what's ultimately important. In this case, if we're comparing 2s to 3d, well, 3 is further out. If we're comparing 1s to 2p, well, 2 is further out. And really, I use this opportunity to emphasize to students that what they had learned about the Bohr model remains true. The further out an electron is from the nucleus, the higher energy it has. The second part of this activity is to ask students what they can infer about the energy of a 4s orbital, since in this example, the 4s is filled before the 3d for calcium. Now, I specifically asked this question because for the longest time in Pennsylvania, and in general, I think the NGSS assessment boundary is main group elements, not transition metal elements. So students don't have to be able to work the d orbitals. But this is always a point of contention, right? Because the 4s orbital is technically lower energy than the 3d. But wait a minute, Mrs. Crosis, you just said that the further out, the higher energy. Well, it gets a little wonky up there. So emphasizing here, though, what can you infer, because they have the evidence in front of them. If this is the correctly filled orbital diagram, therefore, then if 2 electrons are in the 4s and they didn't put them in the 3D, 4s must be lower energy than the 3D. In the image you're looking at here, there's 2 versions of a box diagram where one is filled correctly, but it's showing energy increasing as we move downward, which is totally counterintuitive and just nothing but confusing for students. But I have seen images online where they use this and use diagonal arrows to show guidance as to how you would fill them. Now, guidance to me is like, unless you're going to give a kid that during a test or a quiz or a practice, it's like memorization, right? At this point, they really need to only know potassium and maybe calcium. We're filling the 4s first. But in high school chemistry, we're not going really into that d orbital to fuss over it. And for me in my class, I almost never get to clearly explaining and practicing the electron configuration writing. And so here I'm saying, use this model, use this example that's done up above. And that's like the third thing I want them to work on as an extra challenge. Usually my high achievers will get there and the rest will just not even try, if I'm totally honest. Once they've finished that, we can say, okay, now today is about really sorting out these electron configurations. We want to get to the point where we can learn how to write them using only the periodic table. And that is our end goal of the lesson. Whether this takes you a day or 2, I will warn you, I used to be able to do this in a day, but I really think it probably lends itself better to a 90-minute period. So maybe plan for 2 periods this, depending on how proficient your students are going to be with filling box diagrams and how effective they could be with collaboration should you choose to go that route. So I can use patterns. Use the periodic table as a in the patterns there to more specifically predict and describe location and energy of electrons to more quickly and easily and accurately predict the chemical properties of various atoms. So the why of this lesson, the learning intention of this one versus my introductory lesson, is the predict and describe more quickly, easily, and accurately. Because anybody can fill a board diagram and anybody can do an electron configuration, but if we're going to just look at the periodic table to sort it out, we should be able to get it lickety-split. In this specific lesson, your students are going to fill an orbital diagram for 1 atom if you choose to do the collaboration design piece. You can have small groups of 3. That is what I would recommend for efficiency if you do want to finish this in 1 period and you do have students who are pretty on the ball. Certainly, you have high achievers. You can give them all the activity. They can all do 3. They can all do the analysis, maybe themselves. It's very flexible and completely up to you how you approach this. For me, I ask each student to do 1, and they can look at their partners to see what they did or talk about how they're filling them as they're filling them. They're each doing 1, writing an electron configuration, working together to find a common feature among 3 diagrams and configurations. And then ultimately by the end of class, once you have helped them and guided them through the analysis of these similarities and differences, these patterns and how they seem to map to the periodic table, they can go through a series of skill practice to just identify the location, the properties of that element, and figure out what the end of that configuration would be. So some word walls included here, just to remind students, off-bow diagram, electron configuration, what they are, what they represent. I might use this slide to demonstrate once more, again, maybe for anybody who's absent the day before, as a general overview for students again, the 3 guidelines we're using to fill orbital box diagrams. And I typically will give the example of nitrogen and oxygen here so that I can really drive home that idea of Hund's rule and why Hund's rule matters, and that having unpaired electrons is important and necessary. It's not actually wrong. And the difference between nitrogen having 3 unpaired and oxygen having 2 unpaired, because for some of the models and examples some students will create in this lesson, it doesn't matter if they use Hund's rule or not, because their highest energy electrons don't end in the p orbital. They end in an s, probably. or they otherwise fill a P. So when you're walking around the room and you're taking a look, you wouldn't really know unless they happen to be filling the P at that time. So I do use that opportunity to really drive home Hund's rule because it's the most missed for my students. Here's our task instructions. Now you can see the design of the activity is so that we are looking at metal atoms and non-metal atoms. Groups 1 and 2, groups 6 and 8. 3 represent representative elements from each. And so the idea being that one off-bow diagram is going to be filled in each small group. They're going to observe the diagrams together, highlight similarities and difference, and try to come away with one common feature of the diagrams and the configurations and one big difference. All right, and this is what the artifact outlines look like. So we have elements in group 1A, in 2A, in 6A, and in 8A. What I tell students when they're determining who's going to do what and how, actually, you know the way I did it this year. Let me share this. What did I say here? Each member of a 3-person group will fill one off-bow diagram. So you can do a small group that way. We have 12 here total. If you had 12 or 24 students in a class, that would work nicely. What I did this year is actually I put them in groups of 4, and I had each student complete 3 of them so that we got lots of skill practice with this one task. And so each group then had representative elements from the metals, from the non-metals. So again, lots of flexibility here in providing collaborative learning experiences. Okay, and when I tell them which one are you choosing to do, now if you're splitting up a student per page, 3 students per page, there is going to be a difference. One student's going to have a lot more electrons to draw than another because we're looking at lithium and beryllium with only 3 and 4 electrons, oxygen and neon with only 8 and 10. But if you're assigning one whole page to one whole person and keeping all 4 of these within a small group, then you can say these increase in complexity, they increase in number of electrons as you work from left to right, but every student's effectively doing the same thing and having that same degree of challenge. And then they can all, now the difference there being if the group can work together to sort out similarities and differences within a group. You and I know the similarities and differences within a group are going to be exactly the same. Exactly the same. So of course we get our arrows drawn in, and again, you can deliver this digitally using Seesaw, using Google Slides. I've done it both ways. I also include this as a whiteboard activity in my digital worksheet, where when I sell lessons, they come with the digital worksheets. So even if your student is absent for the day or for the week, or they're making up old work, you can give them that. They can still have the same full opportunity as your in-class students. What I want students to see here, and what we can see naturally in every single rendition, is that 1 electron is the highest energy electron for elements in group 1. And the students may not connect that piece, group 1, 1 electron, but they do see there's 1 arrow in the highest energy orbital. But that highest energy orbital is 2, 3, and 4. They're different. The highest energy orbital, there's only 1, and they live in the S. For group 2, there are 2 highest energy orbitals. They live in the S, but the orbital distances from the nucleus are longer or different, orbitals 2, 3, 4. And same for group 6 and group 8 as well. So we have 4, students will usually say there's 4 highest energy electrons, and they're all in the P shape. They all have the same pattern. There's 2 unpaired for elements in group 6, but they are different distances from the nucleus, and same for group 8. We have a full P level. They're the highest energy, but they are at different distances from the nucleus. And so that's all the students' work. You may or may not go over this individually. I'd probably recommend just making sure students are on track, doing some scaffolding questioning with them one-on-one or in their small groups to get them to this place. But then the slides that follow really organize the data in a way that allows them to see the pattern, identify it, use that evidence. So we take those electron configurations, and this might be where you want to flex a little bit. For me to keep this manageable as a lesson, I need to provide this and say, yes, this is what everyone found. But perhaps you would like students to finish their portions and then contribute to a class whiteboard or on the screen somewhere where they're writing in the electron configurations. That is much more truly a sense of student centeredness, a sense of student ownership. Yeah, I created this lesson. This is our data. We own it. And then have that whole group discussion. What are the similarities you found, group 1? What are the similarities you found, group 2? Or individuals that did the different things. There's some backup slides here because I want to be prepared in highlighting what they're doing. Certainly if I'm in a situation where I can highlight as they talk, that's great. But what we really want to point out is that those similarities have already called out in the box diagrams. They're usually easier for students to see. I do want them, we kind of naturally and ease them into working only with the electron configuration. And highlighting the periodic table in these groups and showing the similarities. Group 1's got that 1 valence electron. They knew that before starting class today. Group 2's got the 2 valence electrons. They knew that before starting class today. Now, in group 6 and 8, that's where it usually comes out, where students are like, wait a minute, oxygen, sulfur, selenium is supposed to have 6 valence electrons, and I'm counting 4 highest energy electrons. And this is where you can really say, well, in the Bohr model, those valence electrons were in ring number 2, right? They were in circle number 2, and that's how it goes here too. Valence electrons actually span the S and the P once we get onto that side of the table. And there's a little bit of work that absolutely needs to be done with students there, sorting through that. But then we can outline for them, go through this guided questioning. What's the highest energy orbital for a certain element? What's the shape and letter? And kind of seeing that I will annotate this table in real time, write the S over here on the 1 and 2, and write the P's over here. We do disregard the D and F. We teach students where it is, like so, but we don't use them actively per the standards and the assessment boundaries. Okay, taking representative elements here, just showing and kind of pointing out, I do a little bit of modeling with the students, identifying the orbital number, showing that it lives in a certain block, and then how many electrons would be in that highest energy orbital. I formalize that process for students to talk through and use going forward. And you can also see there's an annotated periodic table here to show students exactly how we're no longer deferring just to the group number for number of electrons in the highest energy orbital, but the position within the group number. I will even go so far to draw the orbital boxes here and show that there are 3 boxes for P and how 6 electrons fit there, how there is 1 box for X and 2 electrons fit there, how there are 5 boxes for D and 10 electrons fit there. And then we close off the lesson. I go through one of these using polling or whatever situation you might be able to devise, just to see how your whole group is doing with each step, walking through and building for fluorine. So going for period number, highest energy electron shape, number of electrons that live there, and then a double check. This is what it would look like on the orbital box. This is what the end of that configuration would be, and now let's backfill. And then the remaining slides are pulling standardized like assessment examples. Here I give you potassium and magnesium and carbon and sulfur as examples, and they only come from the S and P regions. I give students the checklist of tasks to follow, so if they should need that, because what I like to tell students as I started this video is science is about making mistakes. Class is the place where you're supposed to learn, and so it's okay to be wrong, and it's okay to lean on crutches to help you through. We don't want to be doing that at test time, of course. There's even an exit ticket here, points to an activity I created in Book Widgets where I just chose 6 elements and gave the ending to their electron configurations. It's a simple matching activity. If you have time for that, if you're interested in that, but like I said, when you have a whole library of lessons like this is a prime example of how maybe you could just make this a test question, or make this a homework question, or turn it into a CER somehow. No, it's not completely done for you. It is if you want to use it as an exit ticket, but you can use it as so much more. And I also mentioned that the digital worksheet that contains the entire lesson from objectives and warm-ups straight through the skill practice is also included whenever you purchase this lesson. My next video I post will be leading straight into what I promised students here. It will be leading straight into from electrons in the outermost orbital to chemical properties, to behavior of elements, leading to reactivity and bonding with the octet rule. So we're really going to hone in on all the models we've built at that point. All of this will be prerequisite for that Bohr model, orbital diagrams, electron configurations, all the things. And we're going to lean heavily on developing and using models to do all of the cross-cutting concepts that are listed for science, all in the octet rule lesson.